Hello everyone, hope you guys are doing well. So in today's session, I'm gonna focus on gradient descent algorithm and its classification. First of all, I wanna say that I will not try to elongate this session too much. So that's it. Let's start today's session. Okay. Before jumping onto the main course, let's have a quick recap. I have provided a house price demo dataset to understand the instance vectors. I have also provided the demo vectors. Kindly skim through this slide. Notify me if you have any doubt. I will wait for 20 seconds. Hope you have no more doubt. Let's go to our next slide. In this slide, you can see the hypothesis function using which our model predicts the target variable corresponding to a test instance. Here, I have provided another expression of mean square function, which is our cost function denoted by a function of j parameterized by theta1, theta2 up to theta n. Please check this out. Ask me if you have any query. Okay. So let's move on to the next slide. Here we'll start uh, today's main topic, which is gradient descent. On the right side of the slide, as you can see, there is a general definition of gradient descent. Let's go through with me. Gradient descent is a very generic optimization algorithm capable of finding optimal solutions to a wide range of problems. The general idea of gradient descent is to tweak parameters iteratively in order to minimize a cost function. On the left side, as you can see, I have provided the gradient descent. I have provided the algorithm, the expression of this algorithm. You can skim through this. So I feel uh, I need to explain this to you. As you can see in this equation, that sign containing an ish2 and an equals is actually an assignment operator. Basically, it assigns a new value to the new value of an parameter to the in place of an old value of that parameter. In this case, the new value of the weight parameter theta j is assigned to the in place of the old value of theta j. This is the partial derivative term, and this is the seventh Greek letter. This is called as eta. In this case, in our case, it will be our learning rate. In the next slide, I will discuss about this a lot. Till now, just remind this. Just you have to just note this down that it is our learning rate and it is a very important feature of gradient descent. This is our cost function I have mentioned here, j theta, which is equals to the MSE of theta. As you can see here, this function simultaneously update for every j equals to 0 to n. Here I'm just here n means the total number of features in our in each instance. Okay. uh, in the next in the below you can see that I have provided the gradient descent step for only two parameter, which is theta 0 and theta 1. um, let's check this out. Okay, here is a little task for all of you. Do the partial derivative by yourself and check the result. You may ask for some time. If you wanna do it now. Okay, in the left side of this slide, I have provided the same gradient descent steps for more number of parameters. Please skim through this. If you have any doubt, ask me now, or you can write your doubt in Q&A form. On the right side, I have mentioned the physical significance of gradient descent steps. We can describe gradient descent according to the following example. Suppose you are lost in the mountains in a dense fog. You can only feel the slope of the ground below your feet. A good strategy to get to the bottom of the valley quickly is to go downhill in the direction of the steepest slope. This is exactly what gradient descent does. It measures the local gradient of the error function with regards to the parameter vector theta, and it goes in the direction of descending gradient. Once the gradient is 0, you have reached a minimum. Let's check out the plot on the next slide. Concretely, you start by filling theta with random values, that is called random initialization, and then you improve it gradually, taking one baby step at a time, each step attempting to decrease the cost function, example the MSE, the mean square error term, until the algorithm converges to a minimum. Please check this out. Check this diagram. If you have any doubt, ask me. I will. I will give you 10 seconds to skim through this slide. Okay, let's move on to the next slide. Learning rate, which is denoted by eta. I have told you that eta is nothing but the seventh Greek letter. So there here is a general definition of eta. An important parameter in gradient descent is the size of the steps, determined by the learning rate hyperparameter. If the learning rate is too small, then the algorithm will have to go through many iterations to converge, which will take a long time. Let's check this out. This is the um, plot, and you can see it's taking tiny little steps to go to downhill. I mean, in this case, to our global minimum value. Uh, Due to these little steps and little tiny little steps, it will take a long time. So uh, a time issue has been arised, which should be resolved. Otherwise we have to face many problem in real life because we can't wait for a long time. Okay. Okay, you can skim through this slide. I will give you 10 seconds. Please ask me directly if you have any question or doubt. Okay, let's move on to the next slide. On the other hand, if the learning rate is too high, we might jump across the valley and end up on the other side, possibly even higher up than you were before. This might make the algorithm diverge with larger and larger values, failing to find a good solution. Please check this diagram. As you can see here, the starting point is this, but due to high value of eta, it is taking great steps, larger steps to be specific, and consequently, it is um, it is moved to the next side of the hill, and it is repeating. In fact, we are not converging, rather we are diverging, which isn't a good solution, right? In the next slide we will discuss about one more issue regarding learning rate. So let's jump to the next slide. Finally, not all cost functions look like nice regular bowls. There may be holes, ridges, plateaus, and all sorts of irregular terrains, making convergence to the minimum very difficult. The following figure shows the two main challenges with gradient descent. If the random initialization starts the algorithm on the left, then it will converge to a local minimum, which is not as good as the global minimum. If it starts on the right, then it will take a very long time to cross the plateau, and if you stop too early, you will never reach, and if you stop too early, you will never reach the global minimum. Fortunately, the MSC cost function for a linear regression model happens to be a convex function, which means that if you pick any 2 points on the curve, the line segment joining them never crosses the curve. This implies that there are no local minima, just one global minimum. It is also a continuous function with a slope that never changes abruptly. Technically, its derivative is ellipsis continuous. These two facts have a great consequence. Gradient descent is guaranteed to approach arbitrarily close to the global minimum if you wait long enough and if the learning rate is not too high. Okay, I will give you 10 seconds to skim through this slide. Ask me if you have any doubt. Okay, so let's go to the next slide. In fact, the cost function has the cost function has the shape of a bowl, but it can be an elongated bowl if the feature have very different scales. The following figure shows the following figure shows gradient descent on a training set where feature 1 and feature 2 have the same scale on the left, and on a training set where feature 1 has much smaller values than feature 2. As we can see on the left of the gradient descent algorithm goes straight towards the minimum, thereby reaching it quickly, where on the right it first goes in a direction almost orthogonal to the direction of the global minimum, and it ends with a long march down an almost flat valley. It will eventually reach the minimum, but it will take a long time. This diagram also illustrates the fact that training a model means searching for a combination of model parameters that minimizes a cost function over the training set. It is a search in the model's parameter space. The more parameters a model has, the more dimensions this space has, and the harder the search is. Searching for a needle in a 300 dimensional haystack is much thick, trickier than in 3 dimensions. Fortunately, since the cost function is convex, in the case of linear regression, the needle is simply at the bottom of the bowl. Um I want to add one more point that if you check this diagram very carefully, you can understand the fact that since feature 1 is smaller, it takes a larger change in theta 1 to affect the cost function, which is why the bowl is elongated along the theta 1 axis. Uh, this slide will be provided to you. You can go through this at home at your time, at any time you want. But I wanna give you some time to read this slide. I feel 1 minute will be good enough for you to go through this slide. Please go through this. Ask me if you have any doubt, queries, or anything. If anything seems to be hard to understand to you, please tell me. I will clear this out. Okay, so let's move on to the next slide. The fact: when using gradient descent, if you forget to ensure that all features have a similar scale, example using scikit-learn standard scalar class, you will die. I mean, just there is a little problem, there is a little issue that through this point I wanna mean that you have to ensure that all the features have same scale. Use the scikit-learn's standard scalar class for this. If you don't do this, it will take much longer time to converge, and it will be much longer, and I mean it really. Okay, so let's move on to the next slide. So what's gradient descent? Sorry. So what's batch gradient descent? uh, the partial derivative of the cost function of the batch gradient descent I have provided here in the below section. So uh, you can remember anything? Sorry, can you remember anything? uh, this is exactly what we have learned about gradient descent. Actually, the gradient descent, what we have learned earlier, is nothing but our batch gradient descent. Okay, this MSc, I have mentioned that MSc equals to J, MSc theta equals to J theta. So that's the partial derivative term. In previous cases, I provided the partial derivative for each single instance. Instead of computing these partial derivatives individually, we can use the following equation to compute them all in one go. The gradient vector noted gradient MSE of theta. I mean this term, gradient of theta, of gradient with respect to theta of MSE theta, contains all the partial derivatives of the cost function, one for each model parameter. Basically, it means that once you have the gradient vector which points uphill, just go in the opposite direction to go downhill. This means subtracting this term from theta. This is where the learning rate eta comes into play. Multiply the gradient vector by eta to determine the size of the downhill step. Here is the formula. Though I have written that formula earlier, which was for each single instance. Here we can see the same formula for whole dataset. Okay, so let's jump to Google Colab for some coding implementation. Please wait for some time. Let it be running. Okay, connected. Okay, okay. First of all, I have to import the numpy as np. Just wait for a second. Let it be connected. Uh, in this notebook, I will run few shells for our gradient descent implementation, which is necessary. Next, we will create our some linear looking data set to test our gradient descent equations. Let's import matplotlib.pyplot as plt. Let uh, plot our data set with the target value. So that's a scatter plot. Diagrammatically, it's quite linear, but I wanna focus on a point that you can see this point, right? It feels it has a sense of outlier. Maybe it's outlier. So our topic of discussion is not to treating outlier. I'm just telling it. Okay. Uh, Next, run this also. Okay. Now we have done here. Let's wrap it now. Okay. So now let's look at the quick implementation of the batch gradient descent. This is our eta learning rate, which I have assigned as 0 0.1 uh, in iteration. It means the number of iterations, the maximum number of iteration. M, which is our the total number of instances. I mean the total number of cases in house sale price. It will be total number of houses or total number of instances or cases. Uh, Next, let's start our okay. So I wanna make you to recall one thing, that we started our gradient descent formula by initializing some value to our theta vector. So this is exactly what I have done. I have told you now, what I have told you I earlier. So um, it's as you can see that it's a 2 by 1 vector. Sorry, it's actually 2 by 1 column matrix, which is a vector in our case, and it's a parameter vector, which we will call it theta. Now we are learning a loop. In this loop, we're basically running the gradient descent steps for n iterations time. I mean the number of iterations which we have provided as 100, and it means that this pieces of code will run for 100 times with sorry 1000 times. As you can see here, this is our gradient descent formula. This is our gradient, that partial gradient term. I've Please go through the previous slides. Yeah, if you have any problem, please go to the previous slide at home when you will do it alone. Um, this is our partial derivative term. In fact, this is our expanded form. We we assign that value in the gradient. Then next, this is our learning rate. This is our gradient, and this is our old value of theta, and this whole value will be assigned in theta, replacing the old value. Okay, for your A's, I have provided the gradient descent formula here. Uh, Here it is for two variable. I mean, sorry, two parameters, theta naught and theta one. Please go through this and check this out. Yeah, check this out. This part, and this part. This is exactly same. Okay, exactly same. One thing I wanna told you that that value x 0, okay, which is 1, x 0, whatever the superscript value is, x 0 is always 1. For this reason we can't see any value, any x term here. Okay, so now after the end of the the 1000th loop, we got our finest theta value, which is, oh wait, it isn't defined. Wait a minute. Oh, we forgot to run this loop. Oh. So, as you can see, this is our theta. Not so much impressing. I wanna show you one thing. Just wait a minute. Let's unwrap it. Wait a minute. Wait a minute. Let's run this cell one more time. Check out this answer. Now let's wrap it. Run this cell again. Run this cell. Yeah, it is exactly the same value they're giving us. Check 7214. Yes, 3.72 and 3.14. So gradient descent and the normal equation both are giving the same value, though these values are not good enough. So in this slide, so I mean sorry, so in this shell I am providing some values of eta. First of all, let's run this, then I will explain this. So as you were told in this slide in PPT presentation, that the value of eta, the value of our learning rate, is a very important feature for gradient descent algorithm. This is what exactly happening here. The large value of we have to take a suitable value for eta. It can't be too small or can't be too high. It There is a trade-off in selecting the value of eta. As you can see here, the smaller value of eta takes much less time to converge. I am okay. First of all, let's explain this code. This is actually a function. I've defined a function. The name of the function is uh, plot. Sorry, plot effect of learning rate. This function mainly plot the effect of learning rate in our gradient descent, which takes parameter the eta list. I mean a list where we can provide as much, where we can provide our choices of eta. M, total number of instances in iteration. How many times we want to iterate our gradient descent. It means the maximum number of time. Next, it takes the size of our eta list, which is using the len function, and it is saved in size variable. Next, I define the figure object of using matplotlib figure function. Uh, Next, we run a loop for all values of eta. Here, j will return the order of the loop, which will be in first case, which will be 0, in second case, which will be 1, in third case, which will be 2. And eta in first case will be 0.02, in second case, it will be 0.1, in third case, it will be 0.5. So, at first of our loop, we will create a subplot where we will plot our graph, which is this part. Here we will plot our graph in each loop. In first case it will be here, in second case it will be here, in third case it will be here. Next, we plot our we will plot our data set using scatter plot. Actually, we will scatter plot our data set using plot function, and the feature will be and passing the argument b dot, which refers that our points will be our data set will be plotted as points of blue colors. Next, we are assigning a title to each of our plot. In first case, it will be eta equals to 0.02. In second case, it will be 0.1. In third case, it will be 0.5. Next, we randomly initialized our theta vector using np.random.randn of shape 2 by 1. Please note that it is rand in, not general rand function, which means that our theta will be chosen from standard normal distribution. Next, we run a loop for n iteration time, which means 1000 times. The first step of our loop, we assign our gradient value in this gradients variable. You can see this. It is same as the earlier shell. Oh, actually this, let's see. For in iteration. Next, there is our there I will update our theta value. In the next line, I will predict the y value using this x new b dot theta. I have mentioned this x new biased term before in the previous session, which is nothing but our dataset accompanied by dataset stacked up by the ones of our for convenience of calculation. Let's write this, adding x naught equals to 1. Okay. Next, plot it using a red line. Please note that 𝑥_new is the same which we have used for the previous session. Basically, we will plot, we will evaluate the value for two extreme point and 0 and 2, and for each loop we will run this. Basically, it will be run for n iteration times. Okay, so let's run this loop. Okay, now let's see the result for 100, the result for 10 steps of our gradient descent. First 10 steps, using different values of eta. First, we will use uh, a smaller value 0.02. Next, we will use a mediocre value, and next we will use a large value. Okay, here I have provided a value. I wanna change this now. Let's do it by 0.001 and do it by 0.09 and do it by 0. Let's run this. Okay, this is our data list. If we this is our n iteration times. If you can remember, sorry, this is our total number of instances, which is 100, and this is our n iteration. We will passing 10 as an argument. So our graph, our plot will uh, show us result for first 10 steps of a gradient descent. We're using different values of eta. So I wish to change it using 5. So I am assigning 5, which exactly means that this piece of code will plot the first gradient descent step of using different eta values. Okay, so let's run it. Oh, sorry, there's a problem, I guess. Isn't defined. Okay. It's new b isn't defined. Just wait a minute. I feel I've not run that piece of code. Um, wait a minute. Yes, I have to run this. Yeah, no, it's okay. No, let's run it. Yeah, you can see that for top 5 steps, for first 5 iteration, this using this small value, this plot, this gradient descent algorithm hasn't converged at all. In fact, it is much away from the convergence point. It has came almost near, as you can see, the last step, this one. It has always almost converged, and here we can see an overshooting case. Let's increase the value by 10 and run this cell, and yeah, as you can see, this this is tremendously overshooting, and you can see that this and this the just fall, just notice the change of scale. It is tremendously overshooting, and this is very poor. Change it now. I did 5 and let's add it as now. Let's run this cell again, and this again. Look this, check this out. The change of the scale, it's too much high. See that overshooting, and it has already converged in first 10 iteration. Already converged, you can see the density here. It won't move much from here, and it is almost uh, progressing to the, let's say, the to the minimum global minimum value. Next, change this. Let's play around with this. Just look at this. It is approaching to the minimum value. Just check this density, and it is almost approached. And check this. There's overshooting. Oh, check that scale. So it's basically converging. Yeah, yeah, it's basically converging. Uh, if we put value like 100, it's converging. It's at last it's converging, and it's almost converged. It won't move more, and as you can see, it is converging. It's always almost converged. We don't have to move. Okay, so okay, but now it's good. So let's move on to the next part, stochastic gradient descent. Due to the limitation of time, I will not teach in details of this topic. If you want to learn, please contact me personally. I will provide you materials, provide you proper proper notebook files so that you can understand it very clearly. So let's go through this. The main problem with batch gradient descent is the fact that it uses the whole training set to compute the gradients at every step, which makes it very slow when the training set is large. At the opposite extreme, stochastic gradient descent just picks a random instance in the training set at every step and computes the gradient based only on that single instance. Obviously, that makes the algorithm much faster since it has very little data to manipulate at every iteration. It also makes it possible to train on huge training sets since only one instance need to be in memory at each iteration. Stochastic gradient descent can be implemented as an out-of-core algorithm. Please go through this paragraph. I will give you 10 seconds for that. Okay. I feel you have go through this. So I'm gonna add one more thing that due to stochastic nature of this stochastic gradient descent. Stochastic means random. This algorithm, I mean this SGD, the stochastic gradient descent algorithm, is much less regular than batch gradient descent. Instead of gently decreasing until it reaches the minimum, the cost function will bounce up and down, decreasing only on average. Over time, it will end up very close to the minimum, but once it gets there, it will continue to bounce around, as you can see in this diagram, never settling down. So once the algorithm stops, the final parameter value are good but not optimal. When the cost is very irregular, uh, as we can see in that previous diagram, this can actually help the algorithm jump out of the local minima. So stochastic gradient descent has a better chance of finding the global minimum than batch gradient descent does. Therefore, randomness is good to escape from local optima, but bad because it means that the algorithm can never settle at minima. One solution to this dilemma is to gradually reduce the learning rate. The steps start out large, which helps to make quick progress and escape local minima, and then get smaller and smaller, allowing the algorithm to settle at global minima. This process is akin to simulated annealing, an algorithm inspired from the process of annealing in metallurgy, where molten metal is slowly cooled down. The function that determines the learning rate at each iteration is called the learning schedule. If the learning rate is reduced too quickly, you may get stuck in local minima, or even end up frozen halfway to the minima. If the learning rate is reduced too slowly, you may jump around the minimum for a long time and end up with a suboptimal solution if you halt training too early. Uh, this code implements, and the following code implements the stochastic gradient descent using a simple learning schedule. Uh, this is our code. This is the total number of epochs. I mean the total number of iteration, which will be 50. And this is our learning schedule hyperparameters. This is our learning schedule function, which will take t as argument using this t parameter here. It will return this value to our main function. I mean, in our main driver code. So, as the rule of our, as according to our rule of our gradient descent algorithm, so we have to initialize eta with some random normalized value of shape 2 by 1, which is our random initialization, and next run this whole loop for in epochs, which is 50. In each epoch, we will run this for m time, m equals to 100, the total number of instances. Next, we will randomly pick up a value within m, which will be assigned in our random index variable. Uh, then we'll using that random index, we will select x value and the corresponding y value, and next we will implement our gradient descent step on that specific instance, and we will call our learning schedule of function, and using that we will assign a good value good yeah good value of eta in this eta variable, And next, we will update our theta. So let run this code. Good. Check this out. Yeah, got the value. It's almost uh, equal to this one. It's a little different, but it's okay. Yeah, it's okay. Uh, in this plot, actually, we will see the effect of stochastic gradient descent. Okay. Uh, we will plot this function exactly. Actually, plot first a specific number of training steps to note to make us notice how irregular the steps are. So let's describe this. The number of box, as we have told you. This will plot our data set. Let's run this code, which is exactly same. The difference is here. We will predict our value using the standard formula, and next we will plot this. Okay, so the total number of instances here is 10, and the total number of epochs is 50. Okay, wait a minute. In epochs, I have to change this. Yeah, now it's good. Let's run it. Oh, as you can see this, it's quite impressive. As you can see, it is moving a lot. Let's play around with this. Let's change the value of game. Let's do it 20. Basically, passing this value 20 means that the random uh, point will be selected within index value 20. Okay, not greater than that. And passing a value 100 will mean that the random value um, will be chosen within the index number 100. We can assign any value to it. We can assign 6 here. No, 6 would be good enough. uh, mm, it's 9 here. Let's see what happened. Yeah, as you can see the randomness. Let's put here 80. Okay, let's put here 10. Okay, okay, 10. Let's check this out. So check this out. See the randomness. Note that since instances are picked randomly, some instances may be picked several times for epoch, while other may not be picked at all. If you want to be sure that the algorithm goes through every instance at each epoch, another approach is to shuffle the training set. To make sure to shuffle the input feature and the labels jointly, then go through it instance by instance, and then shuffle it again, and so on. However, this generally converges more slowly. I wanna tell you one more thing, that when using stochastic gradient descent, the training instances must be independent and identically distributed to ensure that the parameters get pulled towards the global minimum on average. A simple way to ensure that is to shuffle the instances during training. Pick each instance randomly on shuffle the training set at the beginning of each epoch. If you do not do this, for example, if the instances are sorted by level, then SGD will start by optimizing for one level and then the next and so on. It will be not settle close to a global minimum, as we can see here. So it's a task for you to do that at home. Use your brain and implement that. In the next cell, we will apply SGD function, SGD regression function, which is imported from sklearn. To perform linear regression using SGD with scikit-learn, you can use the SGD regressor class, which defaults to optimizing the squared error function. The squared error cost function. The following code runs the maximum epochs or until the loss drops by less than 10 to the power minus 3, which I have denoted here as 1e minus 3. During one epoch, I mean total equals to 1e minus 3, starting with a learning rate of 0.1, which is parameterized as 𝜂0 is equals to 0.1, using the default learning schedule, different from the preceding one, which we have built from scratch, and it does not use any regularization, which I will discuss in next sessions during live code implementation. That's why I assign none to the penalty hyperparameter. For more details, please go through the scikit-learn library, the scikit-learn documentation, and go through this SGD regressor function. You can learn more things. So let's run this cell. Okay, let's run it. Yeah, see, it's returning the intercept, which is our 𝜃0, and the coefficient, which is our 𝜃1. Please check the value of the exactly same, almost same, actually almost same, not exactly, almost same. So let's come to the next topic. It will be the last topic of our today's session: minimatch gradient descent. The last gradient descent algorithm we will look at is minimatch gradient descent. It is quite simple to understand once you know batch and stochastic gradient descent. At each step, instead of computing the gradient descent, at each step, instead of computing the gradients based on the full training set, as in batch gradient descent, or based on just one instance, as in stochastic GD, minibatch gradient descent computes the gradients on small random sets of instances called minibatches. The main advantage of minibatch gradient descent over stochastic gradient descent is that you can get a performance boost from hardware optimization of matrix operation, especially when using GPUs. The algorithm's progress in parameter space is less erratic than with SGD, the stochastic gradient descent, especially with fairly large mini batches. As a result, mini batch gradient descent will end up walking around a bit closer to the minimum than SGD. But on the other hand, it may be harder for it to escape from local minima. In the case of problems that suffer from local minima, unlike linear regression, as we saw earlier, shows the path taken by the gradient descent algorithm in parameter space during training. They will end up near the minimum, but batch gradient descents path actually stops at the minimum, while both stochastic gradient descent and mini batch gradient descent continues to walk around. However, don't forget that batch gradient descent takes a lot of time to take each step, and stochastic gradient descent and mini batch gradient descent do would also reach the minimum if you used a good learning schedule. Okay, so with this, let's wrap up today's session. Uh, Please ask if you have any doubt, if you have any question. Thank you.